In this work, we present a theory of joint light and heat transport for Lambertian scenes. Light emanating from a source interacts with the scene in complex ways before reaching the camera to form images. Unraveling the scene information from the scattered light is fundamental to computer vision and imaging. But extracting information only from scattered light leads to several ill-posed problems in computer vision. In this work, we shift our focus to the remaining untapped source of information and make a first attempt to measure absorbed light. When light gets absorbed, it becomes heat. This is best seen outdoors on a sunny day. While the white line markings appear bright in the visible spectrum, the black asphalt absorbs more light, leading to a higher temperature and shines bright in the thermal. As a result, the information lost to light absorption in visible leaks back out in the thermal spectrum. To understand this process, we need to study heat transport. The heat generated via light absorption at a scene point is exchanged with the environment via radiation and convection, and through the object via conduction. Unlike light, heat is exchanged via molecular vibrations and is independent of wavelength. We can observe heat at a point by capturing its thermal radiation that depends only on the surface temperature and emissivity. For objects near room temperature, this radiation is mainly in the long-wave infrared spectrum. Now let's see this theory in action. Consider the following scene. Initially, the scene is at thermal equilibrium. When light is turned on, the absorbed light rises the temperature of the scene, which is observable via a thermal camera. At each pixel, this thermal transient follows a two-parameter exponential curve. Using simple curve fitting, we recover the heat source intensity, which equals the absorbed light intensity up to scale. By processing each pixel independently, we obtain the absorbed light intensity. Since heat transport is independent of wavelength, we can recover absorbed light even for non-Lambertian scenes. To demonstrate the utility of this absorbed light, we consider the problem of intrinsic image decomposition in the visible spectrum, where a given image needs to be separated into its albedo and shading components. This is an ill-posed problem even for Lambertian scenes. At each pixel, the visible image intensity is the product of the surface albedo and its shading, which in turn depends on its shape and lighting. When both shape and lighting are unknown, this shading term can be complex to model, such as for extended sources, interreflections, and in the general case, it can become intractable. But all the complexities of light transport are also present in the absorbed light, which is the complement of scattered light. Mathematically, absorbed light is written as 1 minus albedo times shading. And for the first time, we have measured this absorbed light. Therefore, we simply apply energy conservation at each pixel. For a Lambertian scene, we directly compute the total scattered light from a visible image. We recover the total absorbed light from a thermal video. The sum of these energies is the shading term, after accounting for scale factors, and the ratio of scattered light to this sum is the albedo term. In the paper, we generalize these results to multispectral albedo and camera response. We experimentally validate this theory using a co-located setup of visible and thermal cameras. Using only a short 3.5-second thermal video, we compute the absorbed light intensity at each pixel. Notice that both the albedo and shading components are present in the absorbed light. Using the visible image and the absorbed light, we compute the albedo and shading components using a proposed method. We compare the results against state-of-the-art algorithms. Both the model-based Retinex algorithm and a learning-based ordinal shading algorithm fail to remove the albedo component from the shading terms. To quantitatively evaluate the algorithms, we obtained pseudo-ground truth using images of a painted mask and a blank mask. Their ratio gives the albedo, while the image of the blank mask gives the shading up to scale. When compared against this ground truth, our per-pixel analytical solution outperforms state-of-the-art model-based and learning-based algorithms in decoupling the albedo component from the shading term. In summary, This paper presents a novel approach to measure absorbed light from short thermal videos for arbitrary shapes, lighting, and even for non-Lambertian scenes. Using this absorbed light, we prove that intrinsic image decomposition is a well-posed problem for arbitrary shapes and lighting. Finally, we believe the ability to measure absorbed light without any knowledge about scene geometry, material properties, or lighting uncovers a new perspective to tackling problems in imaging, vision, and beyond. For more details, please visit our project webpage.